today is going to be just an introduction of linear integrated circuits and a little bit of, I could say, a history, different type of linear integrated, different type of ICs, and where linear integrated circuits fits in the IC categories. Okay, so integrated circuits, or IC. An integrated circuit is a circuit in which all or some of the circuit elements are inseparably associated and electrically interconnected, so that is considered to be indivisible for the purpose of construction and commerce. We already know that we have electrical components and electronic components. These are some examples of electrical components. We have resistors, we have capacitors, we have inductors, and we have transformers. And then we have semiconductors, which the majority of ICs are made out of semiconductors. For the semiconductors, we have different type of semiconductors. We have ICs, logic gates, specifically for these. We have transistors. This is actually a bulb, a transistor, the older generation transistors. And we have diodes. For those who had electronics with me, do you remember how many different types of diodes we had? And we went through. We had two main diodes that we use. The power or signal diodes that we use was a PN silicon diode, and we have the Zener diode, which we use for voltage regulation. So we have different type of diodes as well. LED are light emitting diodes, which you see in lightings. That's a different type of diode as well. Diodes are made out of silicon. Specifically, they are made out of two doped silicons, which we call the N-type and the P-type doped silicons. N-type had an extra electron, and the P-type had an extra hole or proton. And transistors, BJT transistors, FET transistors, we went through. BJT transistors are technically the same as a diode. Instead of two semiconductors in a transistor, we have three. One was usually for control, one was input or the source, and the other one was the output. So transistors are usually, again, made out of three type of semiconductors. We had PNP or NPN, and the middle one was usually the control. So if it's a BJT or a bipolar junction transistors, the P was the collector, for example, the N was the base, and the P was the emitter. The difference between a diode and a transistor was the diode is made out of two types of semiconductors. Transistor, a simple transistor, is made out of two. And when we combine transistors, 10 to 100 to 1 billion transistors, we get an IC. And I'll explain the process of building an IC. We also have LEDs, 7 segments displays as well. And we have different sensors, step motors, solenoids, and so on, which again are part of the electronics. In general, electronic components are divided into two different categories. We have active elements and we have passive elements. Active elements, an example of active element is a transistor or a diode or an LED, a photodiode, integrated circuit, operational amplifier, 7-segment, which is technically 7 different LEDs, and a battery. Passive elements like resistor, light detecting resistors or LDRs, thermistors, capacitors, inductors, switches, and variable resistors, and also transformers. The difference between active elements and passive elements is that active elements produce energy by their own, Passive elements don't. Active elements are capable of altering voltage and current and amplifying them, but passive elements are not. An example of an amplifier could be a transistor or an op-amp. Okay. An example of power generating elements would be like a photovoltaic cell, a PV cell. That's also could be an active element. So the difference, again, you can see in this table. Active elements, they produce energy to another circuit in the form of voltage or current. They can control current direction. Passive elements are the opposite. The active elements have function of gain for electronic circuits. They are used for current control and voltage control applications, like a voltage regulator is an active element. And some examples are transistors, op-amps, logic gates, tunnel diodes, and Zener diodes. One note is that a diode may be active or passive, depending upon its property. A normal PN junction diode is a passive, whereas tunnel diode or Zener diode is active components due to their negative resistance property. So if a diode is used to produce light, for example, LED, or to regulate a voltage like a Zener diode, that is considered an active element, but it could also be a passive element when it's used, for example, as a rectifier. Do you have any questions from here? No. Okay. Basics of elements of electronics. We have different components in electronic systems. From power source, we have DC power sources and AC power source, or direct and alternating current. A battery is a source of a DC power source. A generator, like a power plant generator, is a source of AC. Then we have discrete passive components like resistors, capacitors, transformers, inductors, crystals. These are passive components because they don't produce any energy. They also don't control the current and voltage. We have basic passive circuits like the one on the right, left. What type of circuit is this? Yes, perfect. It's a voltage divider. Thank you so much. Great. And we have different type of filters, for example, passive filters, not active filters. And then we have test equipments like oscilloscopes, multimeters. We're going to see and go through them in the lab. Function generators or frequency counters and logic probes. Oscilloscopes are for monitoring AC signals mainly. Multimeters are mainly for, they can also do AC, but multimeters are mainly for DC measurements, like measuring current, voltage, resistance, capacitance, and so on. Function generators are used to generate AC signals mainly, and DC power supplies are for DC voltage. Frequency counters, again, are for measuring AC frequency. Let's go back. So then we have active components like transistors, diode, voltage regulators. We have input devices. Input devices could be sensors like a microphone, like a light detector, strain gauge, temperature sensor, ultrasound. All of these could be a different type of input device, anything that gives us a signal. These are all active devices. Usually they produce a small signal, small voltage. Then we have integrated circuits, and integrated circuits could be digital circuits or they could be analog circuits. Some examples again are for analog circuits would be the op amps, and for analog ICs, one examples could be again amplifiers, a signal amplifier, like what you see on the left here, which is a common emitter BJT transistor with a voltage divider bias. Do you remember this from electronics? This is a full wave rectifier, or what we call a bridge rectifier. And the rectifier, its function is to convert AC signal to DC, generate DC signals. And then we have the output devices, which could be a speaker, a display, a DC motor, step motor, lamp, a server, anything. So the way that we design and construct circuits is usually we design them on a software. First prototype is usually on a breadboard, and I'll explain, and we will go through labs. Those who had already electronic lab with me are familiar with breadboards, but we will go through all of them again. Then we will go on a PCB board or printed circuit board, and finally would be the finishing and the casing and an enclosure of that. And all of that could go into a smartphone, laptop, robot, medical equipment, testing equipment, and so on. So a little bit of review on diodes. Diodes are semiconductors which are used to control the current direction of the current. Diodes are like a one-way valve. This is a water analogy. It's a pretty good way to understand how diode works. So if you have water coming from one direction, it's going to push the valve and open the valve. But if the water comes from the opposite direction, this valve would be closed and the water can't pass. So the water can only flow in one direction. So this is a, and when you're going on the opposite direction, for example, if this is actually rotated this 180 degrees. When water is coming down, it's going to block the current from passing through. We have the diode current voltage curve. This is for a non-ideal diode. For the ideal diode, it's going to look like this. And we had a breakdown. We had the leakage current, and we had the forward voltage. We call this forward bias voltage. This for silicon diode was 0.6, 0.7, and for a germanium diode was 0.2, 0.3 volts. The forward bias voltage is the amount of voltage that it's need to start or jump start the diode. So if we have water coming down here, you need a little bit of water pressure to be able to open the valve. That is called the forward bias voltage. For a silicon diode, again, it's 0.7 volts. For a germanium, it's 0.2 or 0.3 volts. So a silicon diode needs more energy to be able to open that valve. And the breakdown that you see here, or the meltdown, is actually the amount of force that you need to break the reverse bias. What does this mean? It means if I put too much pressure when it's in reverse, what's going to happen eventually? This block point would break. Yes, and this is going to be, again, open. So that's the meltdown point. So in reverse bias, if you put too much pressure on the diode, you're eventually going to break that diode. That's good in some cases, like a Zener diode. We like it to operate in this region because it gives us unique features like control over the voltage. But in other cases, like a signal diode, we don't want to put too much reverse voltage on the diode because it's going to eventually damage the diode. Transistor, again, it's the same as a diode, has an extra doped layer. actually, you can build a diode out of a transistor. If you simply connect these two together, you can make a diode out of a transistor. The water analogy for diode is like this. You have a base current, or the control, I can say. This is the control. And the control, if you give it a small current, it's going to push this to the right. And when that goes to the right, the up part goes to the left. Releases the pressure from here, and it's going to open. The more currents you put in the base or the control, the more you're moving this, and you're going to have a higher current. It's basically like a faucet, I would say. And you imagine you have the source, you have the gate, which is the control of the faucet, and the drain, which is the water coming out of the faucet. And you can control, and this is called a gate in a FET transistor. This is the source, and this is the drain. And the more they open this, more water is going to pass. So if you give it more current, you're going to have more water passing through the faucet and more water to the output. This is for an NPN transistor. We have a PNP transistor as well, which is the opposite direction. Everything is the same between NPN, the NPNP. The only difference between NPN and PNP are the direction of the water flow. So it goes the opposite way again. In the previous one, we saw that we give the current to the base. In this one, the current is coming out of the base, or we're taking the current. So if you have current coming this way, it's going to open this valve, and it's going to open this one, and the water is going to go to the collector or the source in the other case. So a little bit about integrated circuit history. Our class is until 10:20. Am I correct? The theory, okay. In the early days of semiconductors, transistors and other electronic components were available only in individual packages. So you had to buy these separate transistors and connect them together. Let me give you an example. So a normal memory is 8 gigabytes. So each byte is 8 bits. 8 times 8, it will be 64. And giga means 10 to the power of 9. So you need like 3-4 billion transistors to build a normal memory. If you want to lay that down with transistors and build them with transistors, it's going to take an area of Amarillo, even bigger, to build them. So now they've become so small that they literally build a transistor out of 3 molecules. So it's now it's down to 3.5 nanometers, pretty small. But like 30, 40 years ago, 50 years ago, they had to put these individual transistors and wire them together. These discrete components were laid on a circuit board and connected by hand using separate wires. So building a single binary bit of data memory would be more than $2. Now you buy a 16 gig for like $5, $10, something like that. If you want to buy in bulk, it's going to be less than $1. And by the end of the 90s, it was for 5,000 bits, it was a penny. This vast reduction in price was primarily due to invention of integrated circuits. The first need actually for ICs were, and the first push was from NASA and the American Space Program, the Apollo program. And they saw the need to make these circuits smaller, more energy efficient, lighter, and more reliable. The first public discussion of this idea is credited to a British radar expert, William Arnold. But the first IC was actually built by Kilby, which was from Texas Instrument. So basically, Texas Instrument has had this patent for integrated ICs, and the US is the first country to actually build these ICs. But now most ICs are, as you know, are manufactured out of the US, and they're bringing them back. The other day, I had a meeting with the Semiconductor Initiative Institute. So Samsung, TSMC, Texas Instrument, and Intel, all of them, most of them are building plants in Texas. I know that Samsung is building one near Austin, and they said they need 1,500 PhDs by 2027 just to run these. So they have built a lot of these factories, and I will explain a little bit more about these semiconductor factories. TSMC, the largest manufacturer, which is Taiwanese semiconductor manufacturing company. All the iPhone ICs, CPUs are made with TSMC. They build like 95% of all these sophisticated CPUs. Everything you see in the latest NVIDIAs are all made out of in TSMC. They are building a plant, I think it is Ohio, and the problem that they don't have enough skilled workers. So they have to bring skilled workers from Taiwan to train people here. So it's a big market especially for electrical engineering. And I see a lot of them. They asked me to send 3 students for internship for this summer. So if anyone's interested, just let me know. They want to train people as fast as they could to be able to run these. So Kilby started with the first prototype, and the first prototype was actually a you may think it looks very complicated. It looks like this. It's a frequency shifter. So this is the first IC, integrated circuits, and it's made out of a couple of components from wood and some glue. And yeah, this was the first integrated circuit. Around the same time that Kilby was working on his prototype, 2 of the founders of Fairchild Semiconductors at Fairchild Semiconductors, eventually the people worked there, like Moore, went and established Intel, and they called them the Tetris 7 or something like that. They are credited for building Silicon Valley, and the reason that they call it Silicon Valley is because it's the birthplace of Intel, and they started with the semiconductor and the IC. And they were actually the founders of Silicon Valley. They went and actually they invented the optical lithographic machines that are vastly used right now to print and build these ICs. In 1961, Fairchild and Texas Instrument had announced the availability of the first commercial planar integrated circuit comprising simple logic function. This announcement made the beginning of the mass production of integrated circuits. Actually, the first commercial product that came out was a Sony radio. So US actually designed and it built, but the first commercial product that came out, which had integrated circuits, everything before that had separate transistors, but was technically radio and some digital logic gates. So in 1963, Fairchild produced a device called the 907, counting 2 logic gates, each of which consists of 4 bipolar transistors and 4 transistors, so 8 components. The 907 also made use of isolating layers and buried layers, both of which were to become common features in modern integrated circuits. During the mid-1960s, Texas Instrument introduced a large selection of basic building blocks, ICs called the 54XX, and we still use them in the lab in 74 series. If we go to the digital lab, the students that have digital design with me, you will see that to date, we still use the 54 and 74 logic gates, which are the AND, NAND, NOR, OR gates, different logic gates that we have. These Jelly Bean devices each contain small amounts of simple logic. For example, 7400 device contains 4 2-input NAND gates. A 7402 contains 4 2-input NOR gates, and a 7404 contains 6 NOT or inverter gates. TI's 54 and 74 series were implemented in transistor logics or TTLs. And these logics are the basics are every computer that you see, all the computers, CPUs, memories, all of them are made out of logic gates. By comparison, in 1968, RCA introduced a somewhat equivalent CMOS-based library of parts called the 4000 series. And we have 4000 series in the lab as well. So you can read faster than I can. The history continues with building computer components and modern application for specific integrated circuits like memories, RAM, which is a random access memory, ROM, which is read-only memory, and later on become the flash drives that you see, memory flash drives. And then creating the microprocessors and microcontrollers or computer on chips, which was the 4000 series. This is an example of a micro mosaic, Intel RAM and microprocessor. These are the first generations of the RAMs and microprocessors. It may seem complicated, but actually it's pretty simple. It has a few transistors, 24 transistors, so it's not very, very complicated. But it was complicated for the time. Classification of integrated circuits. We have different classifications for integrated circuits. The classification based on the active device, we have bipolar ICs and unipolar ICs. The classification on the application, we have linear or analog ICs. We have nonlinear or digital ICs. The classification based on the technology, we have monolithic tech, which is bipolar ICs or unipolar ICs. And we have hybrid tech and classification based, and for classification based on the application, we have linear ICs or analog ICs, which this course covers, and digital ICs. And classification based on number of transistors, we have the SSI, MSI, LSI, and VLSI. So classification of integrated circuits, ICs, classification according to mode of operation application. ICs are of two types. We have digital ICs and linear ICs. Linear ICs are equivalent of discrete transistor networks such as amplifiers, filters, frequency multipliers, and modulators that often require additional external components for satisfactory operations. Linear circuits are also referred as analog circuits as well. Analog or linear ICs produce, amplify, or respond to varying voltages. I think it's enough up to here for today. We want to also do a small quiz today so you can get familiar with the way that we do our quizzes. For online students, we would have online quizzes that will be posted, and they would have a week to solve those quizzes. So the way that we do our quizzes is going to be, our quiz is going to be through an application called the Kahoot. I don't know if you're familiar with Kahoot. Just give me a second. So the way that the Kahoot quiz works, you have to take, you use your phone, you scan a QR code, and it's a multiple choice quiz. Usually I give out prizes as well. Today is just for learning purposes, but it's both for your attendance and quiz. If you just participate in these quizzes, you get your attendance point, which is 50%, and the next 50% is about the quizzes itself. So again, let's start with the quiz. You can also scan the QR code and run quiz. Did everyone join? So operational amplifier, anything that is an amplifier is an active element. And on the table, you saw that operational amplifier, anything, again, a linear amplifier, linear IC, every IC is an active element, so. Second question, resistors are active elements. Yeah, correct. Resistors are passive elements. They don't produce any power and they don't control voltage or current. By the way, it's time sensitive, so the sooner you answer, it's gonna give you more points. Next question, where is my office? Yep, my office is in room 221J. If you have any questions, please stop by my office. Okay. Thank you so much. It was very nice meeting you all. I will see you on Thursday. And meanwhile, if you have any questions, again, just please stop by my office.